Hello, and welcome to Astronomy 100. In this video, we're going to describe why astronomers seem to build their telescopes on the tops of very tall mountains and kind of remote places. There are some very specific reasons why this is the choice. You'll notice that telescopes are never built in the middle of big cities or in very urban areas, although in the old days that was definitely the case. But we've learned a lot about astronomy since then, and we've chosen to build them in very remote, very high altitude places. So let's have a look at that. Astronomers tend to build telescopes on tall mountains that tend to be in really remote places around the world. And there's a specific set of reasons for this. So let's look at the first reason. The atmosphere, this very atmosphere that we're breathing and that we rely on, is actually a bad thing to astronomy. And the reason is because the atmosphere that surrounds the Earth has the ability to distort the light that passes through it. In this picture here, what you can see is off in the distance is the moon. This is a picture taken by the International Space Station, the people that were in orbit and taking a picture of the Earth and the moon. And on the space station, what you can see when you look at the edge of the Earth here is you can actually see the atmosphere. So the atmosphere that surrounds the Earth is essentially about 65 miles thick, about 100 kilometers maybe. And so it gets very much thinner the higher you go. It's densest at sea level, but becomes thinner and thinner the higher you go up. The problem with the atmosphere is that the light that comes from the stars has to pass through the atmosphere before it reaches us. If you are in space, looking at the stars, then you don't have any sort of a distortion issue because there's no atmosphere. An example is, here is the Hubble Space Telescope, like the space station, and what you would have is the light from a distant object would be seen by this telescope. Because there's no atmosphere, there's no distortion, the curved mirror on the Hubble Space Telescope is allowing the light to bounce and gather, and you get a very nice sharp image of the object that you're studying. Very sharp, very crystal clear, no distortion. But if the light has to make it to the surface of the Earth, the problem is that by passing through the Earth's atmosphere, the light is going to be distorted by the turbulence of the atmosphere. The heating of the surface of the Earth during the day causes hot air to rise, and then at night the cool air descends, and the jet stream and many other factors contribute to the turbulence of the atmosphere. And so the light from the stars has to now work its way through that very turbulent atmosphere. The analogy would be very much like if you were to pop a quarter into a pool, let it settle on the bottom. But if people are playing around in the pool and the water is splashing around, you can't really see the quarter too well. But if you let the water become still and settle over time, then now you can see the quarter at the bottom. So the atmosphere is now very turbulent, and so therefore the light comes in from slightly different directions based on the turbulence of the atmosphere. And when it bounces off the mirror, the light comes to a focus in a whole bunch of different places. And so instead of a very sharp image, you end up getting a rather fuzzy or a very distorted image of the star that you're trying to study. Let me give you a couple of examples. For instance, here's a photograph taken of the sun during sunset. And during sunset, you have to look through a lot of atmosphere to see the sun very far away, low on the horizon. And you can see the layers of the atmosphere distorting the image of the sun. It's nowhere near a spherical body in this picture. And you may have noticed this on a hot day when you look down a hot road and see the shimmering of the appearance of a mirage or what looks like water. So the atmosphere is clearly distorting the image of the sun during sunset. Likewise, looking at the moon during the moonrise or the moonset, you're going to get a very distorted image of the moon. Again, this is the moon rising, and you can see that way off in the distance. Looking through a lot of atmosphere, there's quite a bit of distortion. When you look at stars, it's really no better. This is a photograph of a star. But what you can see is that it's very much distorted, and it's nowhere near a little pinpoint of light that you would expect it to be. Notice how it just seems to be a blob and a bit of a mess of what it should normally be. And that's again because the atmosphere distorting the light. So in astronomy, what we use is a measure of the distortion of the atmosphere, and it's called seeing, kind of a strange term, but the definition of seeing is, as you see on the screen here, is the smearing of an image with the telescope due to the turbulence of the atmosphere. In other words, the telescope is doing its job, it's just that the atmosphere is causing the light to be distorted and therefore the image is smeared. So what astronomers frequently refer to is the night's seeing. What is the seeing tonight? What was the seeing last night? And again, what we're measuring is the quality of the atmosphere and how good or how sharp of an image we're capable of seeing. And the atmospheric distortion changes day by day. It'll be better tomorrow if it's maybe not good tonight, or it was better yesterday, because atmospheric conditions change day by day. The number on the bottom here is showing you the very best that the atmosphere can provide. In other words, if the atmosphere is very still and the turbulence is at its absolute minimum, the best we're able to see is maybe 1 arc second, at the very best, maybe 1/4 of an arc second. So what that means is, no matter how big or how good your telescope is, you're at the mercy of how turbulent the atmosphere is. So maybe your telescope has the ability to see very, very small details in something, but the atmosphere is not going to allow that simply because it has the turbulence and the distortion is built into it, and there's really just no way around that. One of the other problems that astronomers face is what we call light pollution. Light pollution, by definition, is simply the light that we have from cities that shines up in the sky, and the light from these cities will scatter off of the atoms and molecules of the atmosphere. And what that does is it makes the sky have a bit of a glow. And if the sky glows brighter than the stars, then we don't see the stars very well, and we call that light pollution. Here's an example of a city that's using terrible lighting. These lights are not shielded, the lights go off in all directions, they shine up in the sky, there's an enormous glow that is associated with these lights. This picture down here is taken from an airplane where you're looking down on a city from high above, and you can see the clouds below, but even from an airplane you can see the enormous amount of light that's shining up. If you can see it from the airplane, that means the light is shining up and shining at you. So the consequences of light pollution are things like this. Here is the constellation of Orion and some of the details that go with all of the things related to Orion. The Orion Nebula, lots of information around the stars, glowing clouds of gas, etc. But this is taken from a location that has very dark skies. In the city, this is the exact same constellation, but notice how the glow of the sky is really preventing us from seeing any sort of details. So the stars have to be brighter than the glowing sky for us to see them. If the sky glows too bright, we're just not seeing the stars. And you may notice when you go outside in your backyard that you just can't see very much because of light pollution. Another example here is that this is a location that is showing you the difference between being in a city or in an urban area where you get light pollution. Notice the glow of this very distant city is obscuring anything from being able to be seen in the sky. But in a nice, a very, very remote place, you'll have the ability to see everything in the sky. Notice the Milky Way. In the city, you don't get to see the Milky Way anymore because of light pollution. So in nice dark places where there is no light is where you're going to get the best views. And this picture here is just an amazing one. This is the entire surface of the Earth at night taken by satellites. So in other words, photographing the surface of the Earth. And there's no question about the outline of all of the countries of the world. You can see the United States and South America, parts of Europe, all the way. Look at India, one of the highest populations in the world, and look at all the cities. And again, look at Japan and parts of Australia. So clearly in the United States, you're not going to build your telescope in a place where you can't see the stars. So telescopes are built in very remote places. How do we solve these problems? Well, as I said, we build telescopes far from cities, and we build them very, very high up on mountaintops. By being high up on a mountaintop, it solves our third problem, and that's the weather. Sometimes we have clouds that will roll in at night, especially in San Diego, we have these night and morning low clouds. But when these clouds roll in, they cover the city, But any sort of a mountain that rises higher than the marine layer is going to still have very, very clear skies. This is a picture taken from Palomar Observatory, or at least on the way to Palomar Observatory, where you can see that San Diego was basically socked in with cloudy weather, but high above the cloud deck, you still have clear skies. And of course, sometimes rainstorms will come in, but at very high altitudes, you can still be high above those rainstorms. This is a picture here taken from Kitt Peak Observatory in Arizona, and you can see that there's a lot of haziness to the atmosphere, and so the weather patterns and so forth are going to be affected by lower altitudes, or more obvious at lower altitudes. But when you get higher and higher in altitude or higher elevations, you can be high above much of the distortions of the atmosphere as well as the weather patterns. So what astronomers do is they want to build telescopes in places where they can be as high as possible, because being very, very high up in elevation or high up in altitude, you have a very thin layer of atmosphere. The density of the atmosphere is thickest or densest at sea level, and it gets thinner and thinner and thinner the higher you go. If you're on the top of a tall mountain, the amount of atmosphere above you is very thin, and you have the ability to see very sharp images of the stars and the galaxies and the things that you're studying. So being on the top of a tall mountain puts you above the thickest part of the atmosphere, and the stars will be very steady. Being on a tall mountain will put you above some of the weather patterns, and of course it's very common that very tall mountains are very far away from urban areas where light pollution is at its worst. So tall mountains are really the place that you'll find all of the big telescopes of the world. Let's have a look at a couple of examples here. This is a place in the world that has some of the biggest telescopes. This is the big island of Hawaii. And in particular, there's an extinct, or technically it's a dormant, volcano, hopefully that it doesn't erupt again. And the volcano is called Mauna Kea. And at the very top of this volcano, the elevation is it's just about 14,000 feet above sea level. And so even though this is Hawaii, in a nice tropical area, this mountain rises so high that it is high above much of the weather patterns, and at nearly 14,000 feet, it snows on the top of this mountain, even though this is Hawaii. And so some of the biggest telescopes in the world are built right on that ridge line. Here's a photograph. And up until very recently, the biggest telescope in the world was located here in Hawaii. Currently, it's located in a different place around the world. Now, the ultimate solution, of course, would be to put a telescope in space, because in space you don't have atmospheric distortion, you don't have weather problems, you don't have light pollution. But it's very expensive to put a telescope in space, and so we only do that when money will allow. Now, what we're going to do is we're going to revisit Palomar Observatory, and we're going to see what it looks like to see an observatory with all of the telescopes and often various distances and locations. And we'll talk some more about why Palomar Observatory was placed where it was, and of course at the elevation that it is. So let's have a look at that video. So here we are out on the catwalk of the 200-inch telescope, and observatories are often places with more than one telescope, and Palomar Observatory is certainly the case. Back in the 1930s, it was originally planned to have 4 telescopes here on the mountain. The 200-inch telescope, there's a 60-inch telescope, there's a 48-inch telescope, and the very first telescope that was actually put on the mountain was an 18-inch telescope, although it's out of commission today. Observatories are typically places that are on the tops of very tall mountains, and the reason for this is so that we can be as high up in the atmosphere as possible. The idea is that you want to be very, very high in elevation so that the amount of air that's above the top of the mountain is very thin. The problem that we have is starlight that comes from very far away places has to work its way through the atmosphere before it reaches the telescope. And if the atmosphere is turbulent, then the images of the stars become unstable. That creates the twinkling that you might have seen when you look at stars. So if you're down at sea level, there's more atmosphere to look through, there's more twinkling that the stars will have, and it's very difficult to learn things about the stars. Being on the top of a very tall mountain reduces the amount of air you have to look through, and so therefore the views of the stars, the views of galaxies are very steady. In addition to being where the air is very thin, when you're on the top of a very tall mountain, you tend to be in places that are far away from cities. The light from cities is at night something that makes the sky glow, and if the sky glows brighter than the stars, then you can't see the stars, and we call that light pollution. On the top of a remote mountain, you tend to be far from cities, far from city lights, and light pollution isn't as much of a problem. Additionally, being at the top of a very tall mountain means that the weather is something that you can perhaps be more away from the bad weather that typically occurs at lower elevations. We're about 35 miles here from the coast here at Palomar Observatory, and so the air that comes off of the coast is very stable. The marine layer that often covers San Diego doesn't make it up here, and so astronomers can continue to work with clear skies when the city might still be socked in with bad weather. All of these features together are what make it very important to choose the right location, and typically on the tops of very tall mountains will satisfy all of these issues. So you can see Palomar Observatory is a unique place. In the next video, we're going to start to talk about the instruments that astronomers use when they study the stars and galaxies. I hope you'll join me.